We have from the technical university that's pretty great on good speak about it. So different libraries on the plus joyful.
Okay, thanks very much. Great to be here. Yes, so this is joint work with my PhD student, Miriam Mahaman. I would say she did most of the work. I'm just talking about it today here. And I know this is quite a mixed audience here of operator algebras, Hopf algebra people. So we'll see how far we get. I certainly don't intend to go through all those slides, but kind of the first two parts, I want to explain to you the main theorem and roughly the words which are in it. And if we achieve that, I'm happy. And well, the topic is the cusp, which is this curve that you see here, and the ring of differential operators on that curve, and I will tell you what that means. And the claim is that this ring carries a certain algebraic structure, that of a Hopf algebroid, and I will kind of indicate what that means. Okay, let's see. Let's stop working.
Oh, we might have to click on the screen again. Click on the screen with the mouse, and I think it should come.
Click on screen. Okay. Let's see. So yes, indeed. Okay. So the first part is I explain sort of the words which occur in the main result. And well, I talked about curves. Curves are certain affine varieties, certain algebraic sets. I don't know in how far that terminology is known here, but there will be a small k. The small k will always be a field. To be simple, I assume it's algebraically closed and of characteristic 0. If you think k is the complex numbers, you don't lose anything. Okay, so there's a field, and I'll talk about an algebraic set, which means a subset of k to the n, the affine space k to the n, given by some polynomial equations R1 up to Rn as the common zeros of those polynomials. And in particular, that cusp, that curve that we have seen there, is such an algebraic set. So inside K2, the plane, it's given by one polynomial equation, lambda 1 cubed should be lambda 2 squared. You know, that will single out that curve that you have seen on the page before. And as already indicated, my main result will be that the ring of differential operators in the sense of Grothendieck on that algebraic curve carries the structure of a Hopf algebroid. Okay, so feel free to interrupt me at any moment. Tell me if I'm too fast, if I'm too slow.
How important is it that you have this specific equation of the cusp as opposed to some other notion of cusp?
Okay, an excellent question. The point is, so the paper is still not out because while we're typing up, Miriam is improving the result faster than we can type. So indeed, by now we can do it for all cusps. So if you have x to the p equals y to the q, that's also cool. In fact, we can do it for arbitrary numerical semigroup rings. So take any semigroup of natural numbers under addition. So like the one generated by 2 and by 3, take the semigroup algebra, and the ring of differential operators over that will be a Hopf algebroid. But today, I did not intend to mention that even, but Bishan, of course, gets right to the point. Okay, good. Now, recall that when you give me such an algebraic set, then there is something called the coordinate ring. So roughly speaking, it's the ring of polynomial functions on that set capital X. And Hilbert's Nullstellensatz tells me how to describe that. You take the polynomials in d variables. They are kind of the coordinate functions on that ambient k to the d, where the variety was lying. And then you quotient out the ideal of functions vanishing, of polynomials vanishing on your algebraic set. And that will always be the radical of the ideal generated by the defining relations. Okay, so in this way, we get the coordinate ring of our algebraic set, also called the ring of regular functions. So we can interpret these elements as functions from capital X, from the curve to K, which are given by polynomials in the ambient coordinates of the affine space. Okay, So I assume people have seen that at some point. Some nodding. Okay, good. And well, I mentioned already the word affine variety. Some people use affine variety and algebraic set interchangeably. To me, affine variety means it's an algebraic set which is irreducible. So just as you can decompose any topological space into connected components, such algebraic sets can be decomposed into irreducible components. So for example, if you have the defining equation lambda1 times lambda2 is 0, your set capital X would be like the two coordinate axes, and then each coordinate axis is a separate irreducible component of that. And in the case of such a plane curve, the set is irreducible if the defining polynomial is irreducible, as is the case for the cusp, where it was lambda1 cubed minus lambda2 squared. So whenever you have an algebraic set, there is this decomposition into irreducible components, and it's often easier to deal with them separately. And purely algebraically, being irreducible, being affine variety means that this coordinate ring is an integral domain. It's free of zero divisors. And because it's an integral domain, it's free of zero divisors, you can form the field of fractions of that integral domain. So all formal fractions f divided by g, where f and g are regular functions, polynomial functions on my space X, and of course g should not be zero. And we interpret the elements of this field also as kind of meromorphic functions on my space X. You know, of course, g might have zeros, that's fine. So these functions will not have a value in all points of capital X, but still it's in a field that also tells me something about my variety. So for example, when I talk about the cusp, then one can work out that the field of rational functions on that is actually the field of rational functions in one variable t. So it's isomorphic to just fractions of two polynomials, f and g in one variable t, with coefficients in k. No? Under this isomorphism, the one coordinate function goes to t squared, the other coordinate function goes to t cubed. They do satisfy the defining relation that x1 cubed will be x2 squared. They generate what's called the normalization. We'll get to that in a second, literally. And using this, one sees this is the field of rational functions on that curve. Good. And as I just said, there is one more algebraic geometry ingredient that I thought I'll mention, the normalization of my algebraic set of my affine variety X. So this is another affine variety, X bar, some sort of closure operation as it looks, but it's a bit more complicated. So what you can do is you can look at the coordinate ring of X, so the polynomial functions, the regular functions, those with the square brackets, as a subring of that field of rational functions, one with the round brackets, the fraction field. And then in that ring extension, you can ask whether that original coordinate ring is integrally closed. So the integral closure of a subring are the zeros of polynomials with monic polynomials with coefficients in the subring. And usually when you start with the subring of a field, the integral closure is bigger than the subring you started with. You add some zeros of certain monic polynomials. And the ring that you get, the integral closure, is again the coordinate ring of an algebraic set. That follows from a result of Emmy-Noether's, who kind of, well, shows that this is a finitely generated module over the ring you started off with, which then in particular means that it's a finitely generated algebra over K. And then in turn by Hilbert-Nullstellensatz again, you find that it's the coordinate ring of some affine variety. And that affine variety is called the normalization X bar of the original variety X. Okay. And well, geometrically, we now have an embedding of the original coordinate ring of X, my singular curve, into the normalization, the coordinate ring of the normalization. an embedding of coordinate rings corresponds to a map of affine varieties the other way around, just as it would be the case in the correspondence between Hausdorff space and C-star algebras. Embedding of C-star algebras gives you a map between Hausdorff space the other way around. And well, in general, it's not true that an injective map of rings corresponds to a surjective map of spaces. Things are a bit more complicated in pure algebra. But it is true that in this setting here, there will be a surjection from that normalization to the original variety, and it will always be finite to 1. But the number of pre-images might change. So in general, usually the situation is for curves that the normalization kind of is like a covering. And in some points, you glue certain points together, and others, it's 1-to-1. Okay. And well, if the original variety was already non-singular, that is smooth, I will say a few words about smoothness later on. Roughly speaking, well, it means if K is the complex numbers, that what you see is an embedded submanifold of C to the n, an embedded analytic submanifold. So if the original variety had no singularities, was a smooth space, then that normalization actually agrees with the original variety. And if you just talk about curves, then this is actually if and only if. So a plane algebraic curve, you take the subset of points in the plane given by a single polynomial equation, will be singular, well, other way around, will be non-singular if and only if the curve is equal to its own normalization. In other words, purely algebraically, if the coordinate ring of that curve is integrally closed in its field of fractions. Okay. Good. And in the case of the cusp, for example, as we sort of already saw when we talked about the rational functions, the normalization of the cusp is just the polynomials in one variable, or geometrically the affine line. No? And under that identification, x1 goes to t squared, x2 goes to t cubed. And here, in fact, one sees that this map pi is even a bijection. I mean, you saw that on the picture. The picture is, of course, a little bit misleading. Oh, no, wrong direction. The picture is, of course, little bit misleading because here we talk about the real points. So the real curve, not really the complex points, but it doesn't matter which ground field you choose. It is always true that the space will actually be in bijection with the affine line, because you can simply solve equations. Where is it? Here we go. If you give me an element tau of my ground field, I map that to the point tau squared, tau cubed, I get a point on the cusp, and this is 1-to-1, whatever ground field K you choose. So what the picture on the front page kind of suggests is true for arbitrary ground fields. The cusp is just the line, but it has this weird point built in. It's the embedding into the ambient space, which is slightly weird. Okay, good. I think that's all on algebraic sets, coordinate rings, rational functions, regular functions, this type of stuff. Are there any questions on the words that I've used so far? No. Okay, good. So we'll talk about rings of differential operators on curves, and I want them to be Hopf algebroids. That will be the final result. So the next word I'll focus on is Hopf algebroid. Here I will not give you the full definition because it's horrible. I take it that people in this audience kind of have seen Hopf algebras quite a lot and regularly. So I sort of assume people know what a Hopf algebra is. Some people would say quantum group instead of Hopf algebra. And to those people, I would say, okay, then a Hopf algebroid is a quantum groupoid. If you kind of talk about groupoids and describe that by functions, well, then there's maybe not just a single unit map of your algebra functions, but there is the source and the target map of the groupoid, and that gives you 2 unit maps. And in the same way, a Hopf algebroid comes with 2 maps, S and T, called the source and target map, from your base algebra, which replaces your ground field, into the actual Hopf algebroid. And I kind of shorten that up a bit here. So I'll talk about a special situation. There's a very general notion of Hopf algebroid over non-commutative base algebras, and it is even worse. Today, the base algebras will all be commutative, and that makes life a little bit easier. So the situation is always, when I say Hopf algebroid, there will be a K algebra capital A, which is commutative. Think rings of functions on some space, like the coordinate ring of that cusp. And then there will be a ring capital H. That's the actual Hopf algebroid, that is bigger. It contains A as a subring, but A is not contained in the center of H. Right? If H would be an algebra over A, you would want A to lie in the center of H. H can be non-commutative. We don't have that here. So it's a ring extension from A to a bigger ring H, okay? Some people call that an A ring, me being one of those people. And I want that A ring to be augmented. So again, classically, if you work with algebras over fields, you would say augmentation is like a co-unit, a character, a one-dimensional representation, a maximal ideal. So an epsilon which goes from H down to K. And here we want a little bit more. Here we want a little bit more. So we want to map a representation of H on the vector space A. So this map epsilon hat should go from H to the K-linear maps from A to A. And that should be an algebra map. You want the elements of H to act on the base algebra, to have something like a trivial representation, a unit object in some monoidal category that we're going to build. Okay, good. So my Hopf algebroids will have that. And of course, as with the Hopf algebra, there will be a coproduct. And that epsilon hat will be some sort of co-unit for that. And the tricky bit about the definition of a Hopf algebroid is that the coproduct must land in a somewhat crazy space. Well, it's on the one hand, you take the tensor product of H over A with itself, fine. So your maps, your embedding of A into H turns H into a left module over A. A is a commutative ring, so the category of left modules over A is a monoidal category. You take the tensor product of H over A with H, and there will be a coproduct, and H will be a co-algebra, a co-monoid in the monoidal category of A modules. Correct. But even in that setting, H tensored over A with H will not have a component-wise well-defined multiplication in general. And well, in a Hopf algebra, the next step would be you would want that delta to be an algebra map. And that's why for Hopf algebroids, you need to land in this subset of the tensor product of H with itself over A, the subset in which you demand that also when you multiply from the right, things march over to the other side. So in this space, it's a subset of the tensor product of H over A with H. So you have this kind of relation. So elements small a in capital A, the base algebra, march from the left here to the left here. That's by force, by making this tensor product over A. And then afterwards, you realize that there is still the action on the other side, which is not the same because A is not in the center of capital H. And you want that you are also in the subset of those elements where multiplying here from the left gives you the same as multiplying here from the right gives you the same as multiplying here from the right. And that space, that's what's denoted by this symbol here. And a Hopf algebroid comes with a coproduct that lands in that space. Yes, it's the universal A ring, indeed. So you take H tensored AH. Is that chalk? Chalk, yes. So you could take and one way to say it is exactly this. It's the universal subset on which component-wise multiplication is well defined. That's one way to say that. Okay, so there is a coproduct. It lands in a slightly crazy space, but if you're not into Hopf algebroids and quantum groupoids, just think, okay, it's a Hopf algebra where the base field becomes an algebra. And then there's some technical complication coming with that. Yes, of course.
Is recovered by taking A being the ground field.
Yes.
So I'm just trying to see how to reconcile it with the requirement of epsilon head being injective, because then endomorphisms of A over K becomes just K.
No. Did I say epsilon is injective? I never. Oh, okay. Yes. Okay. Very good point. In here, this is okay. In a general Hopf algebroid, you don't need that. So I'm focusing on a certain type of Hopf algebroids where all these things are met. But yes, very good observation. I do consider only those Hopf algebroids for which that representation on the base algebra is faithful. And yes, if you would take A to be K and look at standard Hopf algebras, that would never be satisfied unless H is K, of course. So yes, good point. But that's the crazy thing about the Hopf algebroids. Suddenly this A can become quite big, and it can make sense to sort of look at Hopf algebroids inside the K-linear maps on the base algebra itself.
Sorry, another question.
Yes?
It's again about the co-unit here. So do you have the same axioms that you have in the to collapse the coproduct using the co-unit?
Sorry, Ali, we can't hear you.
Yeah.
Okay. Can you hear me?
Yes.
That's better.
Yes.
So do you have the same co-unit axioms also in this case, like the same co-unit axioms as the Hopf algebra case?
It again got worse. You started well, but then the audio quality descended quickly.
He said, do you have the same co-unit axioms as you would for ordinary?
Can you hear me now?
Yes.
Okay. So the question is, do you have the same co-unit axioms as in the
Yes.
Hopf algebra case?
Yes.
So
Assuming you can see the board, which I don't know is true.
uh-huh.
So we have that epsilon hat, which defines a representation of the algebra H on A. And if you define epsilon from H to A to simply send small h to epsilon of A, epsilon hat of H on 1.
Okay.
So you act with an element of your Hopf algebroid on the unit element of the algebra A.
Okay.
And this map epsilon goes from H to A. And this has to serve as a co-unit for that coproduct. So the coproduct delta together with that epsilon must form a comonoid, a co-algebra in the category of A modules, of left A modules.
Okay, thank you.
Yeah, but one difference is that in general, this map epsilon will not be an algebra map, for example.
Okay.
So this might fail. So
Sure.
it's the interplay between algebra and co-algebra structure, which is a bit messed up.
Of course. Okay, thank you.
Right. And where it gets really crazy is when it comes to antipodes. So this notion of a bialgebroid was invented by many people again and again under different names. So Takeuchi called it cross R bialgebras at the end of the 70s. Ping Shu reinvented it under the name bialgebroid. And there were several others which kind of rediscovered this again and again. And they all ended up with the same kind of definition of bialgebroid, which at first looks heavy, but it's unavoidable. Well, this is what it is. It's kind of the correct definition. And then came the question, well, what about Hopf? What about an antipode? And there are competing definitions. And I would say still up to now, you really have to decide what you want to do with this notion, and then one of the definitions is the right one for you. You know? In our case, it will be a little bit simpler. So we will actually deal with co-commutative Hopf algebroids at the end. Just as for co-commutative Hopf algebras, S squared is the identity. The same will be true for us. We will talk about involutive Hopf algebroids. So there is a map S which goes from H to H. It's actually an algebra antimorphism. That sounds familiar if you do Hopf algebras. It squares to the identity. It fixes the ground algebra, the base algebra A, which lives inside H. Okay, that's also good. And then, well, see already the antipode axiom is a little bit screwed up. And then there's something even worse, which is this. Which is about the fact that usually you would say, okay, the antipode is a co-algebra and an algebra antimorphism. And this is a little bit like this. You kind of get a second co-product, which wants to be the co-opposite co-product. But again, because this base algebra A is not in the center of your ring, things are a little bit messed up. And at the end, this is a definition due to Böhm-Schlachani, and that's the one I'll use. And I suggest don't worry too much. Okay, this Hopf algebroid business, yeah, if we'd go through all the details, it would take us too long. So I decided I keep this short and yeah.
Can I ask for
Sure.
Notation on SPH.
Come again?
So SPH on the right hand side of the equation, what is
Okay, it's just that two brackets. So I take, all right, I didn't say that. This is the epsilon hat. Sorry, we act here. It's the epsilon of S of H, basically. I act with that element on one using the epsilon hat. Okay, very good. That's the other definition of a Hopf algebroid. That's exactly what I mean. There is a, like for a Hopf algebra, you can say in many, many ways when a bialgebra is a Hopf algebra. One thing is take a bialgebra, take the category of modules over that bialgebra, left, that's a monoidal category. That's always left closed. There's always an internal Hopf functor, but in general, that internal Hopf functor will not be compatible with forgetful functor to vector spaces. A bialgebra is a Hopf algebra precisely when it is. The same theorem is true for Hopf algebroids and bialgebroids, but the notion of a Hopf algebroid is not this one. There is no antipode in that one. There is just an analog of the Galois map. You know, there's the whole Hopf-Galois story, which you can carry over to bialgebroids and Hopf algebroids. And when your bialgebroid is a Hopf-Galois extension in the oid world of the base algebra, it's a Hopf algebroid. Yes, and then in that story, you have the Tanaka version nicely. Here it's a little bit more. If everything is finally generally projective over the base algebra, then you can build rigidity here. You get duals of modules because you have a map from H to H up. Okay. Good. So let's suppose we know what a Hopf algebroid is. Something like a Hopf algebra, but out of the ground field, we blow this up to an entire commutative algebra, which can be big. And there's this crazy thing now that the trivial representation isn't so trivial. I mean, exactly the right comment. It should actually be faithful, which sounds crazy. And the example of differential operators is I think, a good one to understand why it's not so crazy. Okay, so what are differential operators? What are differential operators? Well, start with any commutative algebra A whatsoever over K. Okay. View A as a subring of the K-linear maps from A to A, the multiplication operators, the zeroth order differential operators. Okay, the maps which send an element B to A times B for a fixed element A. So in this way, we identify elements of capital A with K-linear maps from A to A. Okay, and then Grothendieck said, let's inductively define higher order differential operators by saying that it's an algebra which lives in the k-linear maps from A to A, and it's the union of filtered pieces, the differential order operators of order up to n, and the zeroth order differential operators, that's just A, viewed as multiplication operators. And then at each step, if I know what the nth order differential operators are, the next higher ones are those whose commutators with multiplication operators is in the next lower order. And in this way, to any commutative algebra A over any commutative K, ground ring K whatsoever, you get some ring, the differential operators. Okay. Let's explore that a little bit more. Let's think about differential operators of degree 1, of order 1. Okay, what would that mean? So, well, order 1 would mean the commutator with any element in A must be of order 0. In other words, must be a multiplication operator. So capital D is my differential operator of order at most 1. The commutator with any element in the commutative algebra should be an element of that algebra, C. This has to be now thought inside the algebra of k-linear operators from A to A. In other words, for every element B in A, we want that first multiplying by A and then applying D minus the other way around. First applying D, then multiplying by A should simply mean multiply by C. Okay, that C, of course, will depend on A, but not on B. That's the key point. And I claim that if we stare at this, we see that actually a differential operator of order 1 splits in a canonical way into a multiplication operator for order 0 and a derivation, a vector field, if you want to. And the multiplication operator is simply the value of D at 1, and the derivation is what you get when you subtract that from D. How do we see this? Well, we simply say, let's see the C from above be partial of A. So in this way, I define a map partial from capital A to capital A. Okay, and then, well, just put in that property up there and see that this partial really satisfies the Leibniz rule. Okay, so in order 1, those differential operators are exactly what you would expect. There's an order 0 part, which is a multiplication operator. There's an order 1 part, which is a derivation, a vector field. The thing is, when you go to higher orders, the embedding of the nth order part into the n plus first order part does not split alinearly. You know, this is something one has in analysis when one learns about pseudo-differential operators and simple calculus and so on. And the same happens in algebraic geometry. It's just not true that a differential operator of order n has a degree 0 part 1, 2, 3, and so on. You can't do that in general. And yeah, and in general, the structure of that ring is pretty complicated. Okay, so, right, I thought I'll talk a little bit more about differential operators and their history. It's now roughly half an hour over, is that right? Okay, good. So the history is quite old, and actually there's an interesting paper from Sweedler, the Hopf algebra Sweedler from 1974, where he develops already a lot of Hopf algebroid theory. It's just that for a few years then nothing happened and no one cared. And Sweedler also started doing other stuff. But the first observation was that if we have a smooth F1 variety X, then this ring of differential operators is what you think it is. Now, what do you think it is? You think it's the universal enveloping algebra of the Lie algebroid or the Lie-Reinhardt algebra of all derivations. Okay, what's going on here? Well, derivations of a commutative algebra are like vector fields on a space. I believe that slogan will roughly be okay here. If not, ask. They are first order differential operators. And now you can start multiplying first order differential operators. And you can take multiplication operators, so elements of your algebra A. You can multiply these guys together, add, and certain rules will be present. Now, for example, you have a Lie bracket on vector fields. That becomes the commutator of those first order differential operators. I mean, that's how it is defined. You can multiply a vector field by a function. Now, the vector fields form a module over A. And that becomes just a multiplication in this algebra of differential operators. And lastly, you can act with a differential operator on with a derivation on a function. And in the algebra of differential operators, there's just a commutator between that first order differential operator given by the derivation and the 0th order differential operator given by the function. And whenever you give me a commutative algebra A and any Lie algebra of derivations that is also closed under multiplication by A, so it's an A module and a Lie algebra over K, you get a universal algebra, which is sort of generated by the elements of that Lie algebra, the elements of A, and those commutation relations hold. And kind of in line with the question about A equals K, if A is K, the ground field, well, then you can't take derivations. You still can take Lie algebras. And then this construction here would give you the universal enveloping algebra of that Lie algebra. So indeed, more generally, here I kind of have an action of the Lie algebra of derivations onto the algebra A, and I built into this slide that this action is faithful, that my Lie algebra consists of derivations of A. Even more generally, you could have a situation where it's some action which might not be faithful. In particular, A could be K. The derivations could be replaced by any Lie algebra acting trivially on K. And then you still have this construction. Yes, so abstractly, when you give me any commutative algebra A, a Lie algebra L over K, L is an A module, and there's some way to map this to derivations by a Lie algebra map. There's a universal algebra, the universal enveloping algebra of that Lie-Reinhardt algebra, or that Lie algebroid as it's called. And of course, these are differential operators. And if X is a smooth variety, all the differential operators arise in this way. In particular, this means the ring of differential operators is in this case generated in degree 1 and 0. Okay, so this was shown by Grothendieck somewhere in SGA 4. And then there's a paper by Nakai in which he formulated what's nowadays called the Nakai conjecture. That's not quite true. So first of all, that paper predates all the others. So the notion of differential operators wasn't there yet. And he also doesn't really formulate a conjecture. He rather poses a question and he says, but nothing is known about this at all. And the question is whether that's if and only if. So Nakai kind of anticipated to some extent, and it's still an open conjecture, which might be true, everyone expects it to be true, that this is an if and only if condition, that if your variety is not smooth, then the ring of differential operators is not generated in degree 1. So once you're away from the smooth case, there are some crazy second, third, whatever order differential operators which you cannot build up from vector fields and functions. And conjecturally, in characteristic 0, I should say that's the actual conjecture that characterizes smoothness. And it's known for curves and a few classes, but not for many varieties. Okay, but of course, the easiest case of all this is the one that you see at the top. If you would talk about the affine line, then the differential operators is the Weil algebra. So there's the variable t by which you can multiply, order 0. There's d by dt, which I denote by partial, order 1. The canonical commutation relations hold. And here, every differential operator can be uniquely written as graded parts. But once more, that's not the case in general. You know, they're splitting the differential operator into parts of a defined order is not possible in general. And at the end, I will show you a presentation of the ring of differential operators on the cusp, and you will see it's horrific. Okay, so it's irrelevant for me, but just for general educational purposes and entertainment, a little bit more algebraic geometry. The Nakai conjecture is also linked to another big conjecture in commutative algebra, the Zariski-Lippmann conjecture. So if capital I denotes the kernel of the multiplication map of my algebra, so it's a commutative algebra. So the multiplication map from kx, tensor kx to kx is an algebra map. It has a kernel, call that I. Take I mod I squared. That's the so-called Kähler differentials. It's the algebraic analog of differential one forms on my space. And this module, the Kähler differentials, they represent the functor, which assigns to a module M the derivations with values in that module. And in particular, the derivations of my algebra are by very construction of the Kähler differentials, the dual module of the Kähler differentials, the A linear maps from omega 1 to A. And well, I already mentioned smoothness a few times and said it doesn't have any singularities like this cusp or self-intersections or so. But one very slick definition of smoothness is we call X smooth if the Kähler differentials are finally generally projective as an A module, and they have the rank that they should have, the dimension of X defined to be the Krull dimension, for example. Would also be the transcendence degree of that field of rational functions over K. So that's one way to define what smoothness means. And well, in that situation, since this is the dual of a finally generally projective module, it's also finally generally projective. So the derivations of the coordinate ring would be a finally generally projective module. Geometrically, that's very nice because the derivations are the vector fields. So this is simply saying that the tangent bundle of my space X is a locally trivial vector bundle. And for a smooth space, that should be true. And the Zariski-Lippmann conjecture says that's also if and only if. So again, characteristic 0, give me an affine variety, take the coordinate ring, take the tangent bundle, ask whether it's locally trivial. And the conjecture is that's the case if and only if my variety has no singularities. And the Nakai conjecture would actually imply the Zariski-Lippmann conjecture. So that's also known. And it's not too hard to show. Okay. Yes.
So if X is smooth, then we have this finely generated projective KX module structured from the derivations. But if you take the universal, we call it Lie-Reinhardt
Yes.
algebra, is it going to be a KX module as well?
Yes.
And it's regardless of being smooth or not.
Well, it's a KX module, but it's in general not projective. In fact, the very next slide is exactly about that. I mean, it's a natural, yes.
But we can also take the universal enveloping of there as Lie algebra rather than.
Yes, but then you kind of lose the information about what's going on if you multiply a vector field by a function, right?
By constants.
Yes, yeah. Yes. Well, yes, I mean, it's not a subalgebra because you also have the degree 0 operators in, right? If you just take the derivations and you take its universal enveloping algebra, you're missing all the multiplication operators. So it's a bit more. So the construction is you first do, what you do is you take an abelian extension of Lie algebras. You take A with the trivial bracket, direct sum that Lie algebra of derivations, make that a Lie algebra, where the bracket between A and L is coming from the derivation action, take its universal enveloping algebra in the Lie algebra sense, then unfortunately kind of you doubled things because capital A is then in the Lie algebra, but it should be in degree 0. So you then quotient out by the ideal, which makes that happen. And that's the universal enveloping algebra as a Lie-Reinhardt algebra. Okay, right. So the question which just came up is related to exactly this story here. So what Reinhardt did, so Reinhardt was a PhD student of Hochschild. So basically when they had written down the Hochschild-Costan-Rosenberg theorem, which is nowadays talked a lot about in non-Euclidean geometry, Hochschild already asked Reinhardt, his PhD student, to kind of write out de Rham cohomology in that setting. And Reinhardt then invented in his PhD thesis not just cyclic homology, but also Lie-Reinhardt algebras and a lot of other things which nowadays are used a lot. It's just that no one really cared back then. I mean, he wrote basically one big paper, which is absolutely fantastic, where he does a lot of things. Yeah, he kind of didn't create the publicity necessary back then, I guess. He also died in a car crash just 10 years later. He kept writing papers. I mean, I only read 3 of them. They're all fantastic, I think, but not too many. So he kind of settled down in the province, and he was in fact an office neighbor of Sweedler. So when he died, that's when Sweedler wrote this big 1974 article in memoriam of Reinhardt, where he took the ideas of Reinhardt a little bit further. And in particular, already in his thesis, Reinhardt wrote down an analog of the Poincaré-Vilcov-Witt theorem for Lie-Reinhardt algebras. And we should recall back then the Poincaré-Vilcov-Witt theorem wasn't yet there really. There were several proofs around, but they were all quite messy because the diamond lemma hadn't been invented yet. And Reinhardt in his thesis proved that under projectivity assumptions on the Lie-Reinhardt algebra, you know that you have this filtration, and the associated graded algebra is a symmetric algebra of the Lie-Reinhardt algebra. Okay. So that's kind of half of an answer to your question. And here is an even better one. And also back then in the 1960s, the main interest in Hopf algebras came from what's nowadays usually called the Cartier-Milnor-Moore theorem, which is a classification of the co-commutative and co-nilpotent Hopf algebras as the universal enveloping algebra of Lie algebras. And well, when bialgebroids started to become interesting again, Ike Mördijk and Janusz Murczun wrote a paper which extend that result to Hopf algebroids and tell us that also in the Hopf algebroid world, the co-commutative, co-nilpotent Hopf algebroids are precisely those universal enveloping algebras of Lie-Reinhardt algebras. But, and here comes your question, you need to make some projectivity assumptions. So you always have that core radical filtration of the Hopf algebroid, you take the associated graded, and its pieces must be projective A modules. So you need to put such conditions always in to do anything with them. So in that setting, which is about smooth varieties and rings of differential operators which look exactly as we all think, everything is as we think. There is this ring, and it is a Hopf algebroid. It's co-commutative, it's co-nilpotent. And well, if we go beyond the smooth case, all those theorems do not apply. And hence I wanted to know whether for any other ring A, the differential operators also carry a Hopf algebroid structure. So I asked Miriam that when she started her PhD, well, a little bit later. And for a long time, there was no progress. She then worked on something else. But then when she was done, she said, oh, now I'll return to that other question and I won't give up. And I tried to make her a bit stay away from that, but she stuck to that. And now we have a solution. So the point is, if you have a differential operator D on a commutative algebra A, that's a typo here, this should be a curly D of A, then there are, by very definition, this inductive definition, a finite list of other differential operators, EI and FI, such that D acting on a product of two elements of A can be written in this form. So you now say, okay, so the co-product of D is the sum EI tensor FI, right? Totally trivial. That's what I thought a few years ago. But the problem is, this is not unique. The second problem is when you write out such an expression, you need to show that it's in this crazy cross A product that appeared. And well, in the first run, Miriam kind of found one presentation which worked and wrote a Python code which verifies all the axioms. And I say, fantastic, let's write it up. Then she said, no, we need a theoretical explanation. So which we now also have. And as I said, now it's even more general A. You know? But that's the aim of the game. Okay. Good. Okay, how are we doing with time? Very good, very good. So that's no. I think, yes, as I said, there is some final part where it's all about technical details and module theoretic conditions, which I put on the slides in case people want to know. But I think what we want to still see is the formulas. And I think then we'll wrap up. Perfect. So let's go back to the cusp. So as I said, the cusp has this normalization, which is just polynomials in one variable t. And in that way, the coordinate ring A of the cusp becomes realized as polynomial expressions in t squared and t cubed. In other words, it's all polynomials with zero constant term, no linear term. Okay, so that's the coordinate ring of the cusp embedded into the polynomials. The polynomials would be that normalization. And then what will occur is also yet another localization of that. We need the Laurent polynomials. So geometrically, we have that map from the normalization to the cusp. And then in the cusp, we can take the smooth locus, everything except the singularity, take the pre-image in the normalization. And that corresponds to a further algebra extension of the coordinate ring. That's my B up there. And the differential operators on the cusp are expressed as certain differential operators on that localization. The localization B is smooth. So the ring of differential operators here is exactly what we think. It's the Weil algebra, well, where T is made invertible. Okay. And I abbreviate d by dt as partial. So this is just the ordinary derivation of a Laurent polynomial. And now I write down certain differential operators here. So for example, t times partial. See, t times partial is a first order differential operator on the Laurent polynomials, but it keeps an element in the cusp in the cusp. Now, if you take a polynomial without constant term and you apply this differential operators, you again get a polynomial without constant term. So you can then restrict this operator d0 to a differential operator on the cusp. Same is true for t squared d by dt. Okay. And now here suddenly are other differential operators of increasing complexity. And the ingenious claim, which was proved, I think, by Smith in 81, is that these elements are differential operators on the cusp, and they generate the ring of differential operators on the cusp. It's not quite a minimal set of generators, but a one that one wants. And here is a presentation of that ring. Okay, so you see, horrible. Okay, there are the multiplication operators, x and y. They are the zeroth order differential operators, the coordinate functions on the cusp. And then there are these d's and the e's, which are these strange differential operators. Well, some are not so strange, but those second and third order ones are pretty crazy. But with some work, one is able to write out a complete set of relations that they satisfy. Okay. In fact, interestingly, while we worked now on the paper, we found an article from the mid of the 70s by a person called Anne Luddington, who in her PhD thesis also wrote all that out. The paper has 0 citations. So we wondered, maybe it's wrong. I said, let's write her an email. So we sent her an email, and after 20 minutes, there was a reply saying, that's crazy. I mean, I wrote this thing. I've forgotten everything, Uli. I can't tell you anything at all, but no one ever talked about this paper since 1974. But no, I'm not aware of any mistakes, but I also can't tell you anything about the paper any longer. When she switched to education, and that's that. So yeah, I think the story for the PhD students in the room, if there are any, is make publicity. It's necessary. It's not just enough to do good work. Okay, so here is a description of this ring. And now the task was, well, write down the co-product of those elements. And as I said, it's not unique, but Miriam, with her ingenuity, just at some point found this is it. And as I said, using Python, she can verify all the axioms and so on and so forth. Maybe a small thing on the side, the antipode of a Hopf algebroid is not unique. If you talk about bialgebras over fields, having an antipode or not is a property. Either there exists one or not, because the antipode is the convolution inverse of the identity map. For a Hopf algebroid, the antipode is not unique. So there are several choices, and this is the one which is involutive and works. Yeah, so at the end of the day, one gets some crazy formulas. And as I said, there's some theoretical explanation. And I think this is the last thing I'll show. So the theoretical explanation is some ring theoretic properties. So there's a big paper by Smith and Stafford from the 80s on general rings of differential operators on curves. And they tell us loads of fantastic things. And in particular, under the assumptions that you see here, well, the ring of differential operators is a simple ring. So this should speak to the histology people somehow. So it's exactly the same game on the purely algebraic side, right? We could either do primitive ideals, yes, or we could do the opposite and consider simple rings. And then these rings of differential operators popped up. More interestingly, I was talking about the ring of differential operators on the variety X and the ring of differential operators on its normalization. And under the assumptions made, they are Morita equivalent. So the modular categories over these are equivalent. Now, this guy here is smooth. So this thing here is the universal enveloping algebra of Elie-Reinhardt algebra, which is a Hopf algebroid. So the category of modules here is a nice monoidal category. So of course, what one wants to see is that the Hopf algebroid structure here corresponds to the Hopf algebroid structure here in the Tanaka picture. In that this Morita equivalence becomes a monoidal Morita equivalence. And we know that by now as well. So for this, one has to write down certain co-ring structures on the Morita context, and that is also done by now. So yes, we're writing on this paper already for quite a while, but it should be on the archive in the next 14 days, I hope. And yes, so in the new version, this is really kind of the theoretical explanation. And to get these co-ring structures on the Morita context, one kind of has to do something called descent theory. So one can talk about the differential operators on this algebra that are noted by B, the Laurent polynomials. And then these Morita contexts, they live inside a certain subsets, which are bimodules under multiplication from the left and from the right. And one then has to show that the co-ring structure on all the differential operators, which comes from the bialgebroid structure, descends or restricts to those Morita contexts. And there is classical descent theory for faithfully flat ring extensions. And the problem is that this algebra B is not faithfully flat over A. So these theorems don't apply. And then one needs a more crazy module theoretic condition called R local projectiveness, also called universal torsionlessness. And that was then kind of the main work in the last months to show that that certain modules have that property. But my feeling is I'll skip that bit and just stop here.
Very much. Should I start? Do we have questions from the audience?
So in this theorem, is it possible to say what is the geometric intuition behind being a unique minimal ideal in the ring of differential operators? So should we think about J as the data of some kind of system of differential equations with A, or how can we possibly come up with this condition?
Yeah, good question. I mean, yes, I agree. I mean, usually, so if you're, I mean, yes, modules over differential operators is what one calls D-modules. And the idea is indeed systems of differential equations. So that you say, I want to have a differential equation like f prime equals f. In analysis, you would say, this has a solution, e to the x. Well, in algebra, e to the x doesn't make sense. So what do? Well, we invent the ring of differential operators and then quotient out by an ideal and kind of generate a module which contains an element which behaves like e to the x. So yes, when you take the ring of differential operators and you quotient out some j, that usually means you choose some differential equations and kind of satisfy them by brute force. Yeah, I don't know. So what one can say is, okay, so the condition is, for example, not satisfied for the nodal cubic. So it is a strong condition. So if instead of, so I had the cusp, so this was the equation x squared, or rather x cubed equals y squared. And if you deform that further to the nodal cubic, x squared plus x cubed is y squared. For this curve, it is still true that the normalization is the affine line. So the differential operators all still live inside of the differential operators on the lower polynomials, but the condition with the j is not satisfied. So here we do not have this Morita equivalence. So this would be a natural next question to test whether it really hinges on this Morita equivalence or whether we also get a Hopf algebroid structure on this. But no, I'm afraid I don't have a good explanation.
Yeah, so in the beginning, you mentioned that your result extends to cusps of other orders.
Yes.
And we also had that theorem which gives I forgot whose theorem was it? I'm sorry. There was a theorem which gives a complete description of the ring of differential operators on the semi-cubic cusp. Yeah, so, and in the list of relations, the most complicated relations are of the form something quadratic equals to something cubic. Yes, for example, yeah, the third line from the bottom, for example, something quadratic equals to something cubic.
Yes.
Yeah, so when you extended your results to cusps of other orders, have you encountered the same phenomenon, that the relations are of the same pattern?
But that's the thing. I mean, as I said, the thing is always, while we still spend time writing things up, Miriam has ingenious new ideas. So for those other rings, we don't do it with generalized relations. We just have abstract results which kind of ensure these module theoretic properties that I mentioned, this R local projectivity, which then allows us to already say that this core-ring structure of the ring of differential operators on the normalization, or rather its localization, descends to those Morita contexts, and therefore we get a Hopf algebroid structure, but we don't write it down explicitly. And I also don't think that for other rings, there is an explicit presentation in terms of generators and relations. Yeah.
Any other questions in the audience? Questions online? If so, just unmute yourself. And if not, then I'm going to ask a question. It's not very concrete question, but at this seminar, we've heard many lectures about jet
Yes.
jets, non-commutative jets and so on. Is there a jet interpretation behind these differential operators? Can you
Of
interpret them
course,
as
the jet is
factorization?
just the continuous dual of this universal enveloping algebra.
Okay.
So, yeah. So the point is the universal enveloping algebra comes with this Poincare-Birkhoff filtration that gives you a topology. So it makes sense to talk about continuous linear functionals on this. That's the jet.
That's the jet.
And that's also why I think I talked about conil-potent co-commutative. When you look into this Cartier-Milnor business, many people have written this up in the 60s. And in particular, Quillen would speak of co-complete, co-commutative rather than conil-potent. And co-complete is exactly about this geometric interpretation. So for them, the universal enveloping algebra or the Lie algebra is really about distributions on a Lie group or algebraic group, which are supported at the unit element. And that's the jet.
And these differential operators are things which factor through the jet, basically.
The differential operators.
I mean, so if you start with the jets, then you define a differential operator as something you've got the, what is it, the jet map that goes from your sections into the jet bundle, and then you should be able to describe your operator.
Yes, so
with
there's a
factorization.
pairing. There's a dual pairing between a section of the jet bundle and the differential operators. Section of your jet bundle is like a Taylor series, so to say. And you can still feed that into a differential operator.
Is there, if it's you're describing in continuous stream, then you take that what structure?
Yes, but it becomes I mean, you then need completed tensor products. So yes, it's, I mean, a fantastic source for all this Cartier-Milnor is Quillen's rational homotopy theory paper. There's an appendix where he kind of writes out Milnor the right way, as I guess Quillen would have said, which is all topological and tensor products are topologically completed, etc. And then it's kind of obvious that you have this equivalence, because you can then do what you do in quantum groups, right? You can take a derivation and you can take e to the power of that, and you show that there's a bijective correspondence between group likes and primitives in this way. Yes.
So if there were no,
Question. If you take just some groupoid, can you always get a Hopf algebroid of your flavor? By
So
looking at functions?
yeah, so from a groupoid, one kind of has to ask, do I want to talk about the groupoid algebra, generalizing the group algebra, trying to get something co-commutative but non-commutative, or do we want to talk about functions on the groupoid, then getting something commutative? And that's more the thing that we have here. So in my case, I had this source equals target. So this is kind of exactly the groupoid setting would be exactly not source equals target. So you would think, okay, the groupoid, you have a total space of your groupoid, you have the base space, the objects of the groupoid, you have two maps from the total space to the base space, which assign to an arrow, an element of the groupoid, its source and its target. Dualize that situation, go to C-star algebras of functions on this, and then you would have two C-star algebra maps from functions on your object space to functions on the total space. And yes, that would be a Hopf algebroid. Thomas Timmermann has written an entire book on this. Maybe that's the other big advice for PhD students. Don't write books. I mean, when you're an old man and you don't add too much to it, then it's a good moment to start writing books. But to start that too early has ruined almost every career I know. So yeah, in particular, Thomas, right after his PhD, thought he writes a monograph on quantum groupoids. And he has done that, but no.
Okay,
So if that's the last question, then I think we'll thank Uli again. This week, the speaker is Chiara Pagani, who will be visiting us for 2 months from Bologna. And the title of her talk is about to appear. So she will speak about braided Lie algebras of gauge transformations from non-commutative Hopf Galois extensions. So hopefully we'll see you next week.